All right, so we are delighted to have Ahmed Almheiri join us today. He was an undergrad at University of Toronto and then received his PhD from the University of California, Santa Barbara, where his thesis titled The Black Hole Firewall and Top-Down Constructions for AES-CFT won the Winfred and Lewis Lancaster Dissertation Award. So after which Ahmed was a postdoc at Santa Barbara or at Stanford, and then at the Institute of Advanced Studies at Princeton. And finally, he joined the faculty of NYU Abu Dhabi in 2002. And we were fortunate enough to actually have him here in New York City for the past 2 academic years. So Ahmed is known for his work on the CFT correspondence, the black hole information paradox, and black hole firewalls. He was awarded the prize of Emirati's Medal in 2020. He won the very prestigious New Horizons Breakthrough Prize in Physics in 2021 for calculating the quantum information content of a black hole and its radiation, which he may tell us about today. And finally, he also won the Mohammed bin Rashid Knowledge Award in 2024. So without further ado, Ahmed.
Thank you, Monica, for that very kind introduction. It's a great pleasure to be back in New York. I'm going to tell you about some progress on the question of understanding black holes. My talk is titled Quantum Black Holes, and it's going to be about that, how to think about black holes as quantum objects. I'm going to start with baby steps. I'm going to tell you about black holes and everything. Understanding black holes is really at the center of unifying quantum mechanics and gravity. Our current understanding of black hole physics relies on disparate areas of physics, so it's really also unifying topic-wise, where we have to factor in general relativity, quantum field theory, statistical mechanics, chaos theory, random matrix theory, and quantum error correction. I will touch on some of these points in this talk. The one takeaway that you should get out of this talk is the so-called central dogma of black hole physics. This is borrowed from the central dogma of biology, where everything stems from the DNA, and dogma here in the sense of assumption. And it's the following claim, that if you have a black hole in a box, and you were to interact with it by sending and receiving signals through tiny slits, it would be as though you are interacting with a genuine quantum system with a large but finite number of degrees of freedom, and one that is governed by a chaotic Hamiltonian with all-to-all interactions, coupling a few degrees of freedom at a time. So I'm going to try to convince you of this by the end of the time. Next up is black holes and Oppenheimer. I promise this will not take 3 hours. So black holes were first discovered, in fact, just a few months after Einstein wrote down his field equations. And what I mean by that is that the first non-trivial metric that was written down is the so-called Schwarzschild metric, something that at the time people did not realize has all these peculiar properties of black holes. It took really 40 years to realize that. Along the way was Oppenheimer and Schneider's seminal work on continued gravitational contraction, where they analyzed the question of what happens if you have stellar collapse. And they showed that collapse fuels more collapse, hence a continued gravitational contraction. And they noticed this peculiar property that light from the surface of the star progressively reddens and can escape over a progressively narrower range of angles. way we understand that now is that when a star collapses, it forms what is called an event horizon, a boundary that separates everything that can escape to infinity from what is doomed to crash into the singularity. Now, I absolutely loathe this picture because I think it's very, very misleading. A better picture is the one on the right, using so-called, this is a so-called conformal diagram, one in which light travels at 45 degrees. What this makes more clear is that the singularity is not actually the center of the black hole. It is, in fact, a point in time. It is where time inside of a black hole suddenly ends. The way you should think about, well, in some sense, the black hole is the singularity. What happens when a star collapses is that you trigger an instability of space-time itself, and it collapses to form the singularity, a region where curvatures diverge, and I'm sure you've heard of the term spaghettification. As you get closer and closer to the singularity, you get stretched in some directions and squeezed in other directions. Okay, and the event horizon from this picture is simply what separates that which can escape or avoid the singularity from what is doomed to crash into it. There's nothing special at the event horizon. Gravity is not so strong that it sucks you in, as you might have read in popular science articles. Gravity can be arbitrarily weak at the horizon. Okay. It turns out that black holes have something to do with thermodynamics. It was observed in the 70s or the 60s and 70s that the area of the event horizon of a black hole behaves like an entropy. It satisfies a first law of thermodynamics. In particular, a small linear increase in the energy is proportional to a small linear increase in the area with some proportionality coefficient that is related to kappa is some property of the strength of gravity at the horizon. And so if you were to interpret A as S and this coefficient as T, the temperature, it looks like a first law of thermodynamics. Okay, so far maybe these are just coincidences. Well, around the same time, people wondered about the fate of the second law of thermodynamics in the presence of black holes. As an observer in the universe, if something falls into a black hole, from your perspective, that object has disappeared. So what happens to the entropy of that object? This would suggest that the entropy of the universe decreases as things fall into black holes, thereby violating the second law. However, this is what led Jacob Bekenstein to define something called a generalized entropy. So you generalize the notion of what entropy is in the theory of gravity when black holes are present to be the sum of all the entropy in the universe, S out. That's the entropy that we see, plus the areas of all the horizons of the black holes in the universe divided by 4G Newton. Then the statement of the generalized second law would be that the entropy increase, or rather, sorry, the area increase of the horizons is larger than the entropy decrease from when the entropy falls into a black hole. And in fact, this inequality has been proven in many contexts. I forgot to actually cite it by Aaron Hall. So all of this suggests that you should assign a black hole an entropy given by the area of the horizon divided by 4G Newton. This is known as the Bekenstein-Hawking entropy. Here it is in its full glory. Now, you might still be skeptical and be like, is this really an entropy? In the same sense that, is this really some rock formation? And in fact, it passes a lot of checks. So this takes me to black holes and statistical mechanics. We have to be careful about how we define entropy. What entropy is that it is a measure of the size of Hilbert space, or classically of phase space. The way you compute it in statistical mechanics is you define a so-called, well, you consider an ensemble, and you consider, for instance, the canonical ensemble partition function given by z here as a function of beta, which is the inverse temperature, and it's given by trace e to the minus beta e. We know from quantum mechanics, when we have e to the minus iht, that corresponds to time evolution by some time t. But there's an I there. Without the I, you should still think of it as time evolution, but it's a kind of Euclidean time evolution. And what the trace does is that it identifies the initial and final points. So this is a time evolution along a circle. That's the definition of the partition function. Okay. And the way you extract the entropy, statistical entropy, or sometimes I will call the thermal entropy, is by simply acting with this differential operator on the log of the partition function. That gives you something like log of the number of states. For instance, in this situation here, we have a box of gas. Omega, the number of states, corresponds to all the different possible configurations of the gas molecules in the box. That's the standard way we talk about entropy in statistical mechanics. So then the question would be, what is the analog of everything I said, but in the gravitational context? What is the canonical ensemble in gravity? And what are these microstates that are counted by the Bekenstein-Hawking entropy? And here I show you what that number looks like as a function of the mass of the black hole. So if you have a stellar mass black hole, the entropy is 10 to the 77. So there are a lot of microstates of this black hole. All right, now I'm going to define what is called the gravitational canonical ensemble. The first step is to understand what is the Hamiltonian in a theory of gravity. With gravity, the Hamiltonian is a boundary term. It is something defined at infinity. As you know, it satisfies, well, gravity satisfies a kind of Gauss law. From the full law of the gravitational tails at infinity, you can read off the total amount of mass inside the universe. And in that sense, you should think of the Hamiltonian as the Hamiltonian of gravity is defined infinitely far away. Once we have that, now we can just run the machinery of statistical mechanics. We write down the partition function, trace of e to the minus beta times h-ADM. That's the technical name for the Hamiltonian. And as you know, this partition function can be re-expressed in terms of the Feynman path integral. Okay? There's some, for example, you have a particle going in a circle. It's all possible paths that the particle can take. Here it is going to be all possible metrics subject to some boundary condition. What is that boundary condition? It is simply the fact that we have at time is a circle at infinity. This is the Euclidean time that I spoke about on the previous slide. So we impose the condition that you integrate over metrics that have this periodicity at infinity. Now, if we want, we want the entropy of the black hole, so we should consider the partition function evaluated on the black hole background. And what that means is that we have to look for contributions to the path integral where where it is where the metric on the spatial slices is given by that of a black hole, cross this Euclidean time. And there is such a solution. It's called the Euclidean black hole. It is a space-time that caps off at where the horizon would be, and you consider the Lorentzian case. Okay, so here what I'm doing is this is a path. This is an integral. I'm approximating it by a saddle point, namely the one given by this classical solution. Okay, that's just some math. Now I can compute the statistical entropy or the thermal entropy using the same machinery, and I get on the nose area of the horizon over 4 G Newton. Okay, and this is really insane. Okay, this is a mystery. Why is it that a single gravitational configuration produces a large number? So in the case of the gas in the box, you're already counting all the possible ways that the molecules can be in. And here, it was just a single contribution that gave us this large number. This is a puzzle. Nobody knows why this holds. In the case of, there are special cases, for example, in string theory, where for special kinds of black holes, you can actually keep track and find precisely what the different microstates are. That's one of the successes of string theory. Okay, so I argued that you should take seriously that black holes have entropy. But immediately, if you do that, you run into a thermodynamic puzzle. Suppose we compare the following two situations. Situation A, where we have a black hole in a box, or situation B, where we have a gas in a box. For sufficiently large volumes, well, since the entropy of the black hole goes as the area, while the entropy of the gas in the box goes as the volume, at large enough volume, the entropy of the gas will be larger than the entropy of the black hole. So just by thermodynamic reasoning, in order to increase the entropy, there must be a process that takes you from A to B. Classically, there isn't. We know that black holes are the conclusion of gravitational collapse. They just settle and they just stay there. That's the story classically. Quantum-mechanically, the story is different. And that brings me to black holes and quantum field theory. Here, what I'm going to consider is the consequences of studying a quantum field theory living on a black hole background. Now, if I give you a quantum field theory, by that I mean a local quantum field theory, the Hamiltonian of such a theory has gradient terms, dx phi, for example. And because of these terms, the system at lower energies favors more correlation. So the ground state, for example, must be highly correlated at nearby points. And for this reason, the vacuum of a quantum field theory, even locally, has a lot of entanglement of this sort. Across any partition you might choose to draw, there's a large amount of entanglement across that partition. Okay? And the state of the quantum fields is given by something called a thermal field double state that has a form like this. The takeaway here is that there are particles that are entangled across any partition. But now the event horizon is also it's one kind of partition, and hence, given that this is a local property of quantum field theory, it doesn't care about the global structure of the space-time. It only cares about the local physics. And hence this property of entanglement and having these particles entangled, well, existence, the very existence of these particles is also true across the event horizon. This gives rise to Hawking radiation. The horizon separates the entangled particles from each other, and the outside particles they carry away the energy from the black hole. Well, they fly off to infinity, carrying away positive energy. And just by simple conservation of energy, the black hole must shrink. The partners of these outgoing Hawking modes are stuck behind the event horizon of the black hole and are doomed to fall into the singularity. From the outside perspective, if you're looking at such a black hole, it would look like, here are some snapshots. The black hole would gradually shrink and would transform entirely into a bunch of photons and gravitons, gas in empty space. Yes, go ahead.
Does the position of the event horizon also shift as the black hole gets smaller? I'm thinking about
No, it is not.
Okay.
It is not. The thing is, the event horizon is a teleological concept. You need to know where the singularity, what the trajectory of the singularity is, and then starting from that endpoint, draw the past, specifying where the horizon is. Yes.
Let me rephrase the question. Instead of talking about the event horizon, what about if we talk about the apparent horizon? Does the apparent horizon shift?
Let's see. Yes, it does shift. The apparent horizon, if I'm not mistaken, for a evaporating black hole, the apparent horizon, I think, is outside the black hole, and it keeps it. Well, it follows well, in special situations where the evaporation is slow and you don't have any, you don't have a lot of things falling into the black hole. Yeah, if you don't drop anything into the black hole, then the apparent horizon is close to the event horizon and follows it. If you throw something into the black hole, then that's no longer true. The horizon shifts by this definition of you have to keep track using this definition of this teleological concept of the event horizon. And so in that situation, they separate. Any other questions? Okay. Now, so the takeaway here is that black holes are not actually black. They have a temperature. They radiate. And the temperature, named after Hawking, the Hawking temperature, has this form. This is an insane equation. This is the kind of equation that you expect to write down after you've solved all of physics. Right? It unifies so many different things. It has H bar, quantum mechanics, C, the speed of light, special relativity, Boltzmann's constant, statistical mechanics, and G Newton for general relativity, and circles. All right. So that's how black holes evaporate. Yes.
So at the beginning, you had that dE equals TBS.
Yes.
Is that the T that will
Yes.
appear? Okay.
That's the T. Yes.
And the fact that everything is tangled across any boundary presumably means that the radiation must carry information because it's correlated with the things inside.
It's actually the opposite. Because it is entangled with the things inside, the quantum state of the outside radiation is in a mixed state. It's given by a density matrix. And hence, it has more randomness than a pure state. something which is not entangled with anything else. And that's actually the next point I will talk about.
Sorry, what's the temperature for a solar mass black hole?
I don't put it here. It's like 10 to the minus 20 something Kelvin, something like that.
So below 3K.
Yeah. Yeah, these are insane numbers. Okay. So our next stop is the connection between black holes and quantum information. And this is really about the touches on the question that was asked a second ago. This process of evaporation leads famously to information loss. Given that the origin of the radiation is sort of originates locally at the horizon, any information that falls in, if you were to throw in a letter inside the black hole, it doesn't imprint on that. So the radiation does not care about what falls into a black hole. And the quantum state of the radiation outside of a black hole will be in a mixed density matrix. The amount of randomness in this density matrix of the radiation can actually be quantified precisely using information theoretic concepts. In this case, it can be quantified using the so-called von Neumann entropy, minus trace rho log rho. And as a function of time, as you emit more and more, as the black hole emits more and more Hawking radiation, the entropy will simply grow monotonically. In fact, this growth is as fast as it possibly can be. Here I'm plotting the what you can call the thermal entropy of the radiation. Namely, it's the total number, it's the logarithm of the total number of states that the radiation could be in. Okay, and those two curves are essentially on top of one another. So the upshot now is that Hawking black hole evaporation predicts that if you form a black hole, let's say in a pure state, with some information inside, it will evolve into a mixed state of the radiation that knows nothing about what you deposited into the black hole. What we are after is to somehow show that the randomness eventually goes away by the end of black hole evaporation. It is okay for the entropy to initially increase, but it has to turn around eventually and go down to zero. Such a curve is called a page curve, and it's a typical behavior of the entropy of a subsystem of an entire quantum system.
Sorry,
Yes.
why do you need the entropy eventually to go back to zero?
And because by unitary quantum mechanical evolution, pure states should go to pure states. Initially, the system was composed entirely of the black hole in some pure state. It is going to evolve to no black hole and just radiation. Therefore, the state of the entire radiation must also be pure, because we're evolving the system by e to the minus IHT. But that's not what we find, or what Hawking found. And it's precisely because of that entanglement. All of these external Hawking quanta, each of them are entangled with something that was inside of the black hole. Now you might say, but the black hole is no longer there. So what are they entangled with? We will get to that later. But nevertheless, taken at face value, there is entropy at the very end of this process. So yeah, so what we want is this. We want a pure state to go to a pure state. Moreover, we expect that when the entropy decreases, it should track the size of the black hole horizon. It should track the area of the horizon divided by 4G Newton. That keeps track of the number of degrees of freedom of the black hole, and you can't be more entangled than the number of degrees of freedom that you have. And so the entropy of the radiation, no matter how big it is, has a maximum because it's entangled with the black hole and the size of the black hole is decreasing. Okay. All right. Next, I will tell you about the correction to this picture. And that's based on work back in 2019 that involved all of these people from various different institutions, mostly here in the US. So this is where I define the so-called gravitational fine-grained entropy. So this is a new formula that comes about because of some previously overlooked non-perturbative effects in gravity. On the left here, this is the standard way of computing the entropy. You consider some collection of radiation, and you compute, I guess I should have written here, S von Neumann, the von Neumann entropy trace rho log rho. The new formula is here on the right, which says that if you want to, it's the following prescription. If you want to compute the entropy of the radiation, you should consider the entropy of the radiation union a region inside of the black hole called the island, plus the area of the surface bounding that region. Okay? So the entropy of the outside gets a contribution from the inside of the black hole. And I will show you how this, well, I'll give you a flavor for how this thing is derived. Here's the formula more generally. The location of x of the boundary of the surface of this region is determined by some extremization procedure for those that are interested. And the full formula is the minimum between these two possible results.
Sorry, I'm not clear on exactly what the island and this boundary are.
Okay, so I'm giving you a prescription. I want to compute the entropy of the radiation here. The prescription is to say, consider the quantum state not just of this region, but this region and some region inside of the black hole. Okay? So far, I didn't tell you how to pick that region,
Sure.
but there is a way through extremizing the boundary of that region. Show it, basically, you extremize the entropy functional as a function of deforming the boundary of that region, and then that selects for you one such boundary. So imagine that this here is one region, and then we have another region inside, looks like a circle bounded by some surface. And the entropy is the union of the, well, again, two contributions, area plus the entropy of the union of these two regions. But notice something very important is happening here. When we include the radiation along with the island and compute the entropy, the entropy from the Hawking radiation is actually low because this region includes both the particles outside and what they are entangled with. So if I give you two particles that are entangled, and I ask you what is the entropy of one of these particles, if they're qubits, you might say log 2. But if I ask you what is the entropy of the combined system of the two qubits, that entropy is 0. They are entangled with one another. They're not entangled with some other external system. And that's what's happening here. And so the answer for this entropy is dominated by the area of that surface X, which happens to be very close to the horizon. And so you can think of it simply as the area of the horizon divided by 4g Newton. And the full answer for the entropy is that it's not the Hawking formula or the island formula, it's actually the minimum between those two. And so you can plot these two. The island formula, remember, just tracks the area of the horizon, and the black hole shrinks as a function of time. So that gives you a decreasing contribution, while the entropy of the radiation just increases, as we discussed before. Taking the minimum of these two contributions gives you the page curve that we were looking for. The page time is the time at which this turnover happens. Okay, so far I just pulled out this, I pulled this formula out of a hat. So where does it come from? So you might want to be controversial and say, what was Hawking's mistake? So what are these overlooked gravitational effects that lead to these new formulas? I will do it with a set of cartoons. So here's a cartoon of a black hole that is entangled with some radiation far away. These two black dots represents the entire collection of the radiation. It's a cartoon. This is the outside radiation, and this is the inside radiation, and it's behind the event horizon of a black hole, and the dotted line represents the entanglement. Here's a baby version of the calculation of the entropy. It is something called the swap test. This is a tool commonly used in quantum information. The intuition is the following. Suppose I give you a random source or a source that I don't tell you if it was random or not. And you can distinguish, you can tell if this is a random number generator or not by simply sampling the source multiple times and comparing the first result with the second result with the third result and so on. In fact, it's sometimes enough to just sample twice. If the results are different, then you know that there is some randomness to the source. But if they are the same, then it's likely that it's a deterministic source. It always gives you the same result. I'm going to do that check or that test in the black hole context. Okay, I'm imagining I'm sampling twice. What that means is you take two copies of your black hole, each of which is entangled with its own Hawking radiation. And what the swap tests amounts to is considering is comparing this situation with again having these two black holes, but where you've swapped the Hawking radiation of the two systems. So what we need to do is we need to compare these two situations. And this is a baby version of Hawking's calculation, where his main driving assumption was that in computing this overlap, we are still working within semi-classical gravity. The gravitational background does not change by much when I compute this overlap. And so the intermediate contributions in the gravity path integral that computes this overlap is the same background of the two black holes. Now the results in 2019 was simply the observation that when you compute the gravity path integral, there are other contributions that can be important. In particular, there's a contribution that is a wormhole that connects the interior of the two black holes and has this weird effect that it swaps the two interiors. So what that does is that it undoes the swap that you did on the radiation. So here we swap the radiation, and the wormhole swaps the interiors, And so effectively, we're back where we started. So this effect tells you it's an effect that keeps track that there is it that the states are not different. Okay. And again, those two contributions give these two possible curves, and they compete. These are contributions in the path integral, and they compete with one another. As a function of time, as the black hole evaporates, the Hawking answer dominates, that has more weight. And once the black hole is small, the decreasing branch dominates. Okay. All right. The next topic is the connection between black holes and quantum error correction. Okay. So recall that in the island formula, the entropy of the radiation outside the black hole was sensitive to the physics inside. There was this island contribution. In fact, you can show that this means that, in some sense, the interior of the black hole becomes part of the radiation. Let me explain what I mean. From the perspective of somebody living outside of the black hole, they see two systems. One is the radiation flying away. The other system is the black hole itself, represented by the area of the black hole. From their perspective, that's a system with area many degrees of freedom. Okay. Okay. And the claim is that the interior of the black hole is, in some sense, it's a separate system, but one which can be encoded in either the radiation far away or in the black hole degrees of freedom. And the way it works is that before the island, if there is no island, if you are before the page time, then the interior is attributed to the black hole degrees of freedom. But once an island is formed, it is now part of the radiation. And when I say part of the radiation, I really mean that seriously, in the sense that you can do things, operations on the radiation far away, and you can modify the quantum state inside the island. Locality is broken. And okay, and this closely parallels what we know from quantum error correction. And in particular, there exist these quantum error correcting codes, in particular an erasure code, where you can encode the state of you can encode a message into a collection of qubits, a small message into a large collection of qubits, and you can recover that message if you have a smart encoding. It actually doesn't need to be too smart. It can be just a random unitary drawn from the Haar measure. Then you can recover that information from any subsystem that's larger than half. Okay, so here, for instance, and it's called an erasure code because you can still recover the information if you erase 3 qubits, for instance. Okay. This is not just an analogy. There are many more checks or agreements between these two, these two pictures. In particular, we find that the time scale for the information to be retrieved agrees in the two cases. For instance, here here I'm representing, or rather, let me just read what I said, that the time scale for the information, the agreement is consistent with a black hole behaving like a k-local quantum circuit. What do I mean? Here's a quantum circuit representing this U encoding. If it acts on n qubits, you need to evolve by a time which is log n, known as the scrambling time. And that is sufficient to be able to reconstruct the message from any subsystem that is more than half of the entire system. Okay? The upshot is that you need to evolve by such a quantum circuit by at least log n amount of time or steps. In the black hole context, you find that the time that it takes for the message to fall into the island that belongs to some region in the radiation is again precisely log n, where n is now the entropy of the black hole. So this is an extremely non-trivial consistency check. Okay, so that was black. So the next, well, that was a lot of detail, a lot of equations and so on. The next segment is black holes and science fiction. Yes.
Just to check that I understand. So this is basically EPR.
Basically,
EPR.
that's entanglement.
Yeah.
Okay.
So the non-locality is just the EPR non-locality.
No, it is not.
It's not.
No. So EPR non-locality is a correlational statement. It's not that I can act on the qubits here and affect the qubits far away. The operators here continue to commute with the operators there. The entanglement does not change that.
So how do you deal with causality?
Science fiction. So I'm going to give you sort of operationally, how do you see this non-locality happening? And I'm not sure if this is appropriate, but I'm going to show some slides that I used in a public talk I gave somewhat recently.
So, I mean, just to make clear, because there is the interior is the radiation. It's not that you have two entangled systems. I mean, I suppose there is. I mean, it's not because you have these two because you could have two Hilbert spaces. I mean, H1 crosses two, and some entangled state in the two Hilbert spaces. But here you're saying that it's not true. I mean, you have one Hilbert space which describes at the same time the interior and the radiation.
But it is interesting, though, that there's a switch that happens suddenly. Before the page time, they were two independent systems. After the page time, some secret thing happening in the background that has to do with the physics of the interior of black holes, something I might touch on later, that changes this.
And so since we have climbed on mirrors for a while, maybe it's worth saying why you don't believe in the other alternative in remnant. What are the things against? Because it could be that the evaporation stops and you have a tiny little particle with a colossal entropy. Right? I mean,
yeah, that's bad because
it's bad, right?
We would have seen that at the LHC. If such particles exist, that can have well, these are essentially, let's call them black holes. It is extremely unlikely that by colliding protons at the LHC that we would create black holes. But given that the number of such states is proposed to be essentially infinite, then they would dominate all processes that we see, interactions that we see at the LHC. And we don't see them.
But unless only a finite number interacts with protons and the other don't.
No, but then you have to make an argument for why there's a finite number.
No, not a finite number that interacts with some.
No, but this is universal. Everything interacts with it. Like, I don't know what you mean by.
Well, I mean, you have some initial state, right?
Yes.
And given an initial state in any particle system, in any system, there is nothing magical in that. You can create some states and some other states do not appear in the final product because I mean the branching ratios are different for different final states. So you could have branching ratios that are non-zero only for a finite number of these remnants, given the particles that we have at LHC, which are quarks and.
It's hard for me to see, it's hard for me to, given that everything forms a black hole, you collide them, it's hard for me to imagine what the principle would be that makes it coupled to a finite number.
Yeah, I mean, is distasteful. It's, if remnants exist, you can make a black hole of remnants, and then the Bekenstein-Hawking formula doesn't make any sense. So,
Exactly, exactly.
but I mean, is it really logically right? Ruled out?
Let me see, okay. So that's one reason why you might not like them. If you're a fan of ADS-CFT, you also would not like them. I think those are the main two objections. Okay, that's good. Let's come back to science now. Okay. Yes.
I don't know if I understood correctly, but before the page time, the interior of the black hole and the radiation is not. So, and if we observe the radiation, it would not contain as much information as things going inside the black hole, right?
Before the page time, well, at any point in time, the radiation in the interior is always entangled with the radiation outside. What changes is simply the amount of entanglement.
So then after the page time, would we see the change in the radiation itself?
Good. So what you would see is that, semi-classically, you would not see anything different, but you would, in principle, have the ability to be able to learn about the interior of the black hole by doing some operations on the radiation. The interior after the page time now is a subsystem of the radiation.
So, then for us, like the observers outside of the black hole, like whatever the information the radiation hold is somewhat hidden.
It is hidden, yes, it's hidden in like, we don't actually know how it's hidden, but there's a lot of room for different, variations in the times that the Hawking quanta got emitted, and correlations between them, et cetera, et cetera, et cetera. We don't know how to see that in the context of semi-classical gravity, but we believe they are there. Okay, back to science fiction. This is meant to give you actually what the calculations, it's meant to give you an operational way of seeing that the information is actually in the radiation. So, in the outside of a black hole, if you're looking at an evaporating black hole, all you see is that the horizon shrinks and the black hole disappears. Let's talk next about the interior perspective. Okay. What I'm going to do now is I'm going to take a slice of this space-time. Here it is. And the event horizon is given by these 2 points, the 2 opposite sides of the circle. As a function of time, the black hole emits these Hawking quanta given by these arrows. And at the same time, the size of the interior actually grows. Eventually, what happens is that the black hole interior, once the black hole completely evaporates, actually, in some sense, disconnects from our universe. So here's a nice picture. Here's our universe. Here's the interior. It buds off into a baby universe, just swimming in the void. Now, let's imagine we have some information inside that baby universe. How do we extract? Can we extract it? How do we see it? So imagine that George Martin finally finishes his book, and then he throws it into an evaporating black hole, and that black hole evaporates away completely.
This is science fiction that he finishes the book.
Yes.
What's
Okay.
the timeline on the evaporation?
Okay. Okay. So the way that you can read that book is by forming a separate black hole, a second black hole, which is also evaporating. And the claim is that there's a process that you can do. You can collect 1, Yeah, you build a factory which collects the radiation from those two black holes. And there's actually something concrete that you can do, which induces the creation of a wormhole from the interior of your black hole and the baby universe that's not connected to our universe, which swaps the interiors. Remember that what I talked about in the entropy formula, and can retrieve the book. And then now, unfortunately, if you're dying to read it, or if you're literally dying to read it, you have to jump in. How am I doing on time? 5 minutes. Okay. Sounds good.
But why can't you simply, I mean, if you collect the radiation and then have some decoder?
Yeah. So the rules are still not clear. So this is one way that we know how to do it, but in principle, there should be a way where you extract it and have it in your hand outside. But it's not clear that it's going to have a semi-classical picture associated to it. Here we can actually, this is a process which has a space-time semi-classical picture that we can talk about. Yeah. Okay. All right. So, all right, the next topic, okay, this is going to be very quick, is the connection between black holes and circuit complexity. Remember, a black hole is a quantum system, and it evolves with e to the minus I hd. Imagine you have a black hole in a box. As a function of time, as we saw on the previous slides, the interior grows. But also, we also argue that you can think of a black hole as a collection of qubits, whose time evolution is given by some quantum circuit. And the conjecture, or a conjecture, is that the analog or the interpretation of the growth of the interior of the black hole corresponds to the circuit complexity that prepares the state, so to speak, of the black hole. Okay. The last thing I wanted to mention is the connection between black holes and chaos. And we all know what chaos is. It's a statement of, it's a sensitivity to initial conditions. We've all experienced that when playing a game of pool. In this setting, it's the following situation. Imagine you have a black hole with a Hawking quantum very close to the horizon, which is meant to escape the black hole and arrive at your lab at some time t. Imagine that sometime in the past, a butterfly flaps its wings and it creates a small perturbation that falls into the black hole. What that will do is that it will slightly increase the size of the horizon, which will then capture the Hawking mode that was meant to escape to infinity. And hence you will not see it in your lab. And you can compute the function, well, for this calculation, what you do is you compute the probability as a function of delta t, the time at which you throw the perturbation, and you find that it has this form. The probability is 1 for small delta t, and then it decreases exponentially initially, characteristic of chaotic systems with some of the Oppenheimer exponent lambda. In this case, the Oppenheimer exponent is 2 pi over beta, and it is something that you expect, rather, for a local system. This is, in fact, is the largest that the Oppenheimer exponent can be. It is as chaotic that a system can be. So in some sense, black holes are the most chaotic objects in nature. Okay, the last point is black holes and the inside. There's a question mark because this is still an open problem. So we discussed mainly the outside perspective, that if you interact with a black hole, it's as though you're interacting with a quantum system. The inside, the rules are not so clear. For instance, here's a wild idea about how the inside works. Something called the final state proposal. The quantum mechanics inside of a black hole is modified. You have post-selection. The singularity, in some sense, projects the state of the interior onto some specific state. And one can use that projection actually to, this makes some sense, because you can use it to teleport the information from the inside of the black hole to the outside, using the entanglement between the inside radiation and the outside radiation as a resource. The information can do that for the experts. Okay, that's really everything I wanted to say. So just to recap, so black hole physics remains a rich and stimulating field, bringing together many different areas of physics. There are many open problems. What are the microstates of a Schwarzschild black hole? Is there an analog of the central dogma for the interior? Does quantum mechanics change in the interior? And what role does a singularity play? There's definitely more to do here, and perhaps some of you will author the next chapter of black hole physics. And so I'll leave you with a question of black holes and
You mentioned that the black holes grow as a function of time. My question is, which time? Who and how is the time? Who measures the time? And who measures the size of the black hole? And how is it being measured?
Depends on the situation. First, irrespective of your definition of time, it is a fact that if you consider Cauchy slices that go into the interior, as you propagate these Cauchy slices to the future, they grow. The size of that Cauchy slice grows. That's a fact. In the context of ADS-CFT, there are you can compute. Let's say we're in the context of a wormhole, not a black hole. So it's a two-sided object. You can compute the correlation function between the two sides, and that is sensitive to the distance between the two sides, between the two exteriors of the wormhole. That's a more say operational. Operational is not the right word, but that's something you can calculate, and it can tell you what the size of the wormhole is. Question back?
So there was a claim in black holes and quantum error correction that the interior of a black hole is a separate system, one that can be encoded in the radiation or the degrees of freedom. How did that how did that happen?
It is a.
Could you repeat the question?
If I may clarify, how does the interior become part of the radiation? Or how does it switch between being a part of the black hole, being a part of the radiation? All I can say is that maybe one answer is that it's an observation. From the entropy formula, you can, whether or not the island contribution appears, tells you if the island is part of the radiation or not. And this the science fiction part, that is something that in the phase where you have the island, there is an operation you can do, which can reach into the black hole and probe the island region.
So this is just
Those are connected. Yes.
So this is just from the island contribution to the entropy.
Correct.
Okay.
Correct.
You had two pictures. One is the conformal diagram where you have a singularity at the end of an evaporating black hole, and the other in which instead it bubbles out. So are they connected? I mean, can you write
Yeah.
also a conformal diagram for this?
No, I cannot. So that's actually something I'm thinking about right now. So this picture, this is faster. Okay, maybe this is faster. Okay. This picture is actually a fiction. This is this final transition between having a black hole to not having a black hole. So far does not rely on any calculations, or not based rather on any calculations. I suspect that this is a comment for the experts. You might be familiar with this work of Jianbing Yang and Douglas Stanford, and also Phil Sard, that the emission of a baby universe causes the length of space-time to shrink. So perhaps what happens at the end of black hole evaporation is that you emit a baby universe, which contains the interior, and then that causes the length of space-time to shrink to that. So perhaps there's something like that, and I'm analyzing this in the context of 2 dimensions. We can talk about that.
Among the things you mentioned, what do you think would be the closest that would lead to a concrete observational signature of any kind? And a related question is, you mentioned the butterfly flapping its wing, and it's all chaotic. We live in a universe filled with stuff, and at the minimum, 3 Kelvin radiation. So how much does all that stuff, mess up with all the beautiful math?
Yeah.
All that stuff?
Well, see, when I talked about chaos, I had this picture of a perfectly set up billiard balls. So if you don't give me that ability, then I can't really probe this notion of chaos. Okay. Your first question. Realistically, right? So as you know, there's big hype on building quantum computers. There's something that I did not talk about, although I kind of alluded to, that a gravitational system, well, I said that a black hole behaves like a quantum system. In fact, this is precise in this thing called ADS-CFT. There's conjectured duality between certain quantum mechanical systems whose dynamics mimic that of black holes. You can imagine trying to simulate these systems. Some of them are very simple, like a bunch of spins interacting with one another in some complicated way, which conceivably can actually be put together in a quantum computer. But so far, we're waiting on the engineers to solve that problem, to building a quantum computer, and then one can construct these things and well, ask it whatever question you might have. Correlation functions of certain operators at the boundary, which probe the geometry of the supposed dual black hole. And the exciting thing is that it would be giving us would be a direct probe into non-perturbative physics, just because whenever we do these calculations in gravity, we often take the semi-classical limit, where we take G Newton to 0. But in this case, and G Newton really corresponds to 1 over the number of degrees of freedom in the dual system. So we're taking infinite number of degrees of freedom. But non-perturbative physics is accessed when that n is small. And that's convenient when you're building a quantum computer. The n's they're pretty small. But I'm sure it's not going to be that simple, but that's the closest thing I can think of.
So you said the horizon was in some sense it's not real, right? But then later on you said in the interior of the black hole we may need to modify quantum physics, right? Quantum mechanics. But with that, like if you went across the horizon and then quantum mechanics worked differently somehow, then you were across the horizon. That seems contrary to what we learned in like general relativity 101.
Yeah, so that's why it's a hard problem.
So you're saying you are saying that the horizon could be something very real. and-
No, that's
Okay.
not what I'm saying.
Okay, then,
Well, what is very real is the singularity,
yes,
and it's the effect of having the singularity to your future.
okay,
In some sense, what I want is that the semi-classical physics that we expect continues to be true inside of a black hole. But somehow the presence of the singularity is what guarantees that. Like, for example, this thing we talked about in screen hour, that the same arguments that gave us the page curve, etc. If you apply them to a closed universe, will tell you that a closed universe has the Hilbert space of a closed universe has dimension equal to 1. That is not the claim is that that's true, but also that you living in a closed universe have experiences, and effectively the dimension of the Hilbert space of the systems that you interact with and so on is larger than 1. And we expect that the singularity has a role in that. Somehow it allows for the Hilbert space here to have a large dimension, but in such a way that the full interior has small dimension. Yeah. That's why you should work on it.
All right. There's still one more question?
One final question?
So you mentioned a click, like every black hole goes out of the click.
Every black hole?
Every black hole's going through a click so that it reverses. Like eventually the entropy will all go to 0, but can a black hole have that like the click kind of reverse so that it might have multiple peaks?
It can, if you throw something into it.
But by the way, too, maybe it was obvious, but this behavior of the page curve is what happens if you have a lump of coal that burns. It's exactly the same. The curve will be exactly the same. You have a piece of coal, it has a lot of entropy, I mean, that contains a lot of information. When it burns and it's no longer there, all the information is in the radiation and in the decay products. So from this point of view, the page curve is what makes the black hole, as seen from the outside, look less strange and look more like any other quantum system.
Exactly.
Great, let's thank Ahmed.